Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about how to soup up your telescope. I'm delighted to have with us Dr. Bradford Behr, astronomer and optical engineer. In 1992, he got his bachelor's in astronomy from Williams College in Massachusetts. And in 2000, he got his PhD in astrophysics from Caltech. From then until 2003, he worked at the McDowell Observatory in Texas, and from 2003 to 2007 at the U.S. Naval Observatory here in Washington, D.C. Since 2007, he has moved off into the private sector, bringing spectroscopy down to Earth. Welcome back to this table.
Thanks, Kent. It's great to be back on the show.
All right. What can we do to soup up our telescope?
Right. Well, telescopes are very good for gathering light, bringing it to a focus. But for amateur astronomers who just want to stargaze, you put an eyepiece there, you look at whatever pretty astronomical object you're interested in. But professional astronomers are interested in measuring that light, analyzing it in certain very specific ways to try to learn more about the universe. And sometimes just taking a picture with a digital camera is useful. We've talked in previous shows about spectroscopy, which is breaking the light up in all its component colors, and you can learn a lot about stars, planets, galaxies.
Well, especially the chemistry of
the chemistry of stars.
Yeah, that's right.
But today I wanted to talk about three other sorts of instruments, analysis devices that you might put on a telescope to give it special capabilities to enhance its view of the universe in one way or another.
All right.
So
now the first one was adaptive optics.
Adaptive optics, taking the twinkle out of stars, which sounds very unromantic, but it is extremely useful for science to give you a sharper view of the universe around us. The Earth's atmosphere has a blurring effect.
Yeah.
It's sort of like those heat waves you see out over a parking lot on a hot day. Everything gets all shimmery. And looking at two closely spaced stars or the center of our galaxy, that shimmering effect blurs out a lot of the interesting details. So
it's because the atmosphere does not have a uniform density.
Exactly.
There's fluctuations in density.
Right, there's bubbles.
Rippling.
You can think of them as bubbles of hotter, slightly cooler air, and that changes the density. And so the light, as it's traveling down through the atmosphere, gets deflected. Right. Most people like to think of light as a ray, a little line that's shooting along, but an alternative way of looking at it is as wave fronts, sort of like the waves on the ocean. You think of the wave crest traveling along. Right. So a distant star would have evenly spaced, very flat wave fronts coming down. As soon as that hits the atmosphere, the wave fronts get all distorted and ripply. Right. Some parts slightly ahead, some parts slightly behind.
Right.
So, so there's this technique called adaptive optics, which originated both in astronomy and in the defense establishment.
This was part of the what was called Star Wars.
Right. The Strategic Defense Initiative. Right. That Reagan kicked off. They had the opposite problem. They wanted to shoot lasers.
Shoot powerful lasers
up through the atmosphere,
to shoot ballistic missiles,
shoot
warheads,
missiles, right? or
warheads.
Enemy satellites. Keeping that laser beam focused onto a target was difficult with this distortion from the atmosphere.
Right.
So they figured out a way to have what's called a deformable mirror, a metallic surface that's thin enough that it can bend, and lots of little motors behind it to change the shape of that mirror to precisely counteract the ripples that the atmosphere was going to impose. So taking those distorted wavefronts and straightening them out again, flattening them out so that you get a nice sharp view of of the star or planet you're looking at.
Well, now the amount of deformation of this mirror has to be very small, some fraction of a wavelength of light.
You need that level of control,
Yeah.
But going through many dozens of miles worth of atmosphere, the amount of distortion might actually add up to several waves, even hundreds of waves.
Oh.
So these deformable mirrors have to adjust their height over a range, and it's still quite small, a millimeter or less, but with very, very high precision in order to properly take the twinkle out.
Wow, a millimeter would be like 2,000 wavelengths. That's,
Something of it, yes,
yeah.
just about that.
Wow. Okay.
So it's a very mechanically challenging job, also very computationally challenging, in order to make this measurement and then quickly calculate what the correction is. It's not something you do once. It's something that the system has to do hundreds of times a second in order to keep up with the twinkle.
So that twinkle is like 100 hertz.
Yeah, or even higher. I think cutting edge AO systems, adaptive optics systems these days, go up to 500 or even 1,000 hertz in terms of how quickly they can correct. And then there's also tying into the Star Wars, the SDI context, the idea of sending a laser beam up through the atmosphere to help make that measurement. You can, if you have a very bright star in what your telescope is looking at, in your field of view, you can use that. You can say, well, okay, this star looks all blobby. It should look really sharp. So what do we need to do to make it sharp? And then everything else in the nearby area in the sky also gets sharpened up.
Right.
But if there isn't a convenient bright guide star, as it's called, you can take a laser beam, shoot it up the direction that the telescope's pointing, and it'll bounce off a layer of sodium atoms high in the atmosphere and create an artificial guide star. Of course, you have to be careful that there isn't an airplane flying over when you're shooting this laser up here. So it's only the very remote observatories on top of mountains in Chile or on top of the volcanoes in Hawaii that are permitted to do this laser guide star technique.
Yeah.
But the net result is quite impressive. Some images of the center of our galaxy, which were currently just a big fuzzy blob, get resolved into many individual stars, and these stars are close to the black hole that we know is at the center of our galaxy.
Right.
And measuring over periods of years, you can trace these individual stars in their orbits around that central point. Images of the planets, particularly looking for faint stars next to bright stars, which we'll talk about more in just a moment.
Let me just ask, the alternative is to put your telescope into orbit.
Yes.
So you're not looking through the atmosphere.
Get up above all the turbulence.
But Hubble cost billions, and some of the other orbiting telescopes for
similar prices.
Does adaptive optics have an advantage there?
It does. It's not quite as expensive, although it is still very technically challenging and takes a lot of high-tech equipment, but it is cheaper than sending something into space. The other advantage is that
you good in terms of optical quality?
And a lot of the AO systems that are currently operational give sharper views that are as sharp, if not sharper, than Hubble. The other advantage of staying on the ground is that you can generally build much bigger telescopes.
Right.
And the diffraction limit, the smallest possible spot that you can measure, is sharper, is smaller, the larger your telescope aperture. That's just a basic law of physics.
Sure.
So, a 10-meter diameter telescope like the Keck with a good AO system can potentially get 4 times sharper view of a given object than Hubble, which is only roughly 2.5 meters in diameter.
Right. That's
so,
impressive.
I guess the third advantage is if something breaks, you can fix it a lot more easily.
Oh yeah.
If it's down on the ground, then not having to send the shuttle up for a house call.
Right, which is very costly.
Yes, yes indeed.
Wow. Your second way of souping up your telescope.
Turbocharging it, as it were.
Yeah. Coronography.
Coronography, a coronagraph, is a add-on to a telescope, a special instrument package attached to the tail end of the telescope at the focal plane, which lets you more easily see faint objects next to bright objects.
Okay.
Typically, if you are looking at a bright star, there's this glare around it, and sometimes even spikes. It looks, again, it's very artistic, it's very photogenic, but there might be something interesting hiding behind those spikes.
For example, something perhaps orbiting
Exactly.
very near the bright star.
A fainter star that's a companion to the bright one, or even planets. And this coronagraphy was invented back in the early 20th century in order to look at our sun, and particularly the faint outer layers, the corona of the sun, which normally you can't see because the disk of the sun is so bright. So it's sort of an artificial eclipse, if you will.
Right.
But that same approach has been adapted to nighttime telescopes, and it turns out to be particularly useful looking for planets. Now, we know of hundreds, up to thousands now, of planets around other stars, but nearly all of those were discovered via indirect means, either looking for the spectroscopic wobble in the star, or occasionally the planet going in front of the star and blocking a little bit of the light.
So what you're really saying is that if it's a binary system, then the star that you're looking at is wobbling. It's moving closer
Exactly.
and further away.
Doing a little gravitational do-si-do, and you can use spectroscopy.
So a Doppler shifting,
see a Doppler shift,
blue
right.
and red and blue and red.
And that's very
Yep,
useful.
yep.
You can measure properties of the planet that way, but you're not seeing the planet directly.
You're inferring it.
You're inferring it there.
Yeah.
So it's really nice to be able to combine these techniques to be able to see the planet directly as well as infer its mass through this indirect wobble method. And the problem being that planets are typically, as we know, planets shine from the reflected light from their star,
Right.
and that means that they are anywhere from 1 million to 1 billion times fainter than the star, and very difficult to see from the just taking a picture directly. So this coronagraph, it's a lot of complicated optics inside the telescope that block the light from the star, and not just the direct light, but all of this diffracted light that would bounce around inside the innards of the telescope.
It's what you call stray light.
The stray light and the diffraction patterns. Just for instance, putting an opaque black disk at the focal plane won't suppress all of the light from the star, because light has a habit of leaking around edges.
Right.
It's called
Diffracts
diffraction
around.
effect.
Yeah.
So there are multiple stages to a well-built coronagraph, and
But you would black the inside of the telescope to try to absorb some of that stray light.
and various other light baffling techniques. The upshot then is that you can make the light from the star go away almost completely and see any faint objects that are in its immediate vicinity. And then if they're planets, you measure over periods of months or years, and you can see them marching around in their orbits, maybe even get individual spectra of those objects to see what sort of gases might be in their atmospheres.
That's a neat trick.
It is a very neat trick, and it's often combined with adaptive optics, because if you can get the Earth's atmosphere blurring effect at least reduced, if not eliminated, then that makes the coronagraph work that much more effectively. So using this technique, astronomers, actually a friend of mine in grad school was part of a team that discovered the first brown dwarf using a coronagraph at the venerable Palomar telescope, the 200-inch. And
now, brown dwarf would be a star that's not quite heavy enough to ignite.
Right, it's a failed star.
It's a failed star.
Or it's sort of midway between a star and a planet.
Right, so it doesn't have that fusion that's keeping it warm.
Right, a little bit of fusion very early on in its life, but then it kind of, that fuel source runs out very quickly, and it just fades away, and is mostly detectable from, well, depending on where you're looking at. In the infrared, it still is glowing faintly, like the embers of a campfire, but for visible light, you only see it from the reflected starlight. So getting the light from the star to disappear, or at least reduce it enough that you can see this, it's a firefly next to a spotlight. And brown dwarfs, a lot of planets are now being picked up with this coronagraphy technique.
Oh boy, this is quite impressive.
It's very neat, the whole idea of instruments, different instrument packages dedicated to a specific scientific measurement that you can then, it's like having a huge, beautiful telephoto lens if you're a photographer, and then having different camera bodies you clip onto the back depending on what kind of photos you want to take.
Right. Well, I think in terms of one of the science is, I've always kind of wanted to know the chemistry of some of these newfound planets, partly because I'm curious to see if they could support life.
Right.
So,
and we are just now starting to be able to do that. One of these combined AO coronagraph systems, again back on that Palomar 200-inch telescope, has picked up has been measuring a known 4-planet system, and has been able to isolate spectra of each of the 4 planets, and they're very low resolution and low signal to noise. So there's a lot of static in those measurements, but it still looks very suggestive, very likely that there is a certain type of gas in one of the planets and not in the others, methane, a lot of the same sorts of spectral patterns we see from the gas giants in our own solar system.
Right.
Jupiter and Saturn and Uranus and Neptune are hinted at by the data that has been collected, and that'll only improve as they make further measurements and refine the system.
All righty. Polarimetry.
Right. So a lot of our audience, I suspect, is familiar with polarized sunglasses.
Oh yes.
The glass is made in such a way that light that's oscillating in one direction gets through, and light that's oscillating in the other direction is blocked.
Right.
And that's useful because light that's reflected off a body of water or off of the highway in front of you tends to be the side-to-side light gets reflected well, and the up and down light gets absorbed.
A chromed bumper or something like that.
Yeah, is very strong. So with a set of sunglasses, they set the polarization so that the reflected light tends to be blocked, and you can see more clearly.
Yeah.
Out in space, things can get polarized as well. The light from a flat surface, say the icy surface of one of the moons of Jupiter, will be polarized. The disk that orbits a big black hole in a quasar can have polarization characteristics. And magnetic fields are a very good way to create a polarized signal. As electrons are trapped in the magnetic field and are spiraling around.
Spiral along the field lines.
Yep.
Right.
And so they're oscillating preferentially in one direction, and that can create polarized light or polarized radio waves.
Synchrotron radiation.
Synchrotron radiation is one example
which
of
is
that.
polarized.
Right.
Yeah.
So a polarimetry system inside a telescope is actually a lot simpler than the AO and the coronagraph we were talking about. It's often just a piece of glass that has a polarization characteristic to it. It'll let one orientation through and not the other orientation.
So it's like a filter.
It's a filter. And then you rotate it, and you see, okay, it looks brighter at this orientation and fainter at this orientation. That means some fraction of the light is polarized along this direction. And then you do that at a bunch of different places in a gas cloud, for instance, and you can see these, essentially, it's like sprinkling iron filings on it.
Right.
You can see the field, the magnetic field lines.
We've had that as children in grade school. You
Right.
put a magnet on the table, then a sheet of paper over it, and then you sprinkle the filings.
And they tend to line up.
They tend to line up.
And show you the north to south field line. So you can do the same thing indirectly with photons. And this magnetic fields play an important role in how gas clouds collapse to form stars and form solar systems. Other situations where a supernova has exploded and there's this shell of gas traveling outwards. It will often carry a magnetic field along with it, and
because it's ionized gas, and ionized material tends to carry the field lines with it.
Exactly. It's sort of sticky for magnetic fields. So
in our own sun, there's coronal ejections, flares, I guess.
flares, sunspots are magnetic phenomena, and so polarimetry, as in the case of coronography, polarimetry was at first done almost entirely when looking at the sun in order to measure, to see where those magnetic field lines were and how that influenced the motion of all the turbulent swirling about that you see on the sun's surface. But it has since been adapted for nighttime astronomy and looking at many other interesting objects other than the sun. So now these are kind of niche applications. Not every astronomer is interested in polarization because not all astronomical objects show polarization signature.
Right.
But if you are looking at something that's got magnetic fields, or if you're particularly interested in faint things next to bright things, you either find a telescope that's got one of these systems on it and sign up for you. Say, I have this project, I'd like to make use of your polarimeter to measure X, Y, and Z, and then when it's your turn on the telescope, the crew, the permanent technical staff at the telescope bolts on the system that you want to use, and you make your observations and then analyze the data.
Okay.
And occasionally you build your own. If there's something that doesn't quite do what you want it to do, a lot of astronomers are part-time engineers and design their own AO systems or polarimeters or coronagraphs to make it work just right for what they want to study.
Now, the satellites that we sent out, for example, to Jupiter and to Saturn, have reported strong magnetic fields.
Right.
Because they carry a magnetometer along
That's
with the satellite.
a direct measurement.
That's a direct measurement.
Right.
Can you see polarization effects on these two planets?
I think so. More so, I believe, in the radio waves that are coming from those planets. I'm not aware of any optical
I understand that aurora effects have been seen through telescopes. You know what I mean? Where,
right there.
Charged particles enter into the upper atmosphere and create a glow.
Right.
And I was wondering if that might have any polarization.
Good question. I don't know, but I would imagine if there are charged particles and magnetic fields involved, there's going to be some sort of polarization signal. Whether it's strong enough to be measured is a different matter. But if we can't measure it now, I suspect some future generation of polarimeters that's much more sensitive would be able to see that. The technology is always marching onwards, and who knows what 20 years will bring in terms of being able to create new instruments that could attach even to current telescopes.
Now, I was thinking if we can go back to the adaptive optics question, the computer resources that are required to determine how to move the flexible mirror, the deformable mirror, what kind of computing are we talking about here?
It's, 20 or 30 years ago when this technique was first started being developed, you needed close to supercomputer powers in order to do it's a matrix inversion for those of you who are math oriented. But computer technology moves even faster than most other sorts of technology.
So I was wondering, is this, in terms of floating point operations per second, we're talking millions or billions? Or?
I think we're probably up to the high megaflops or gigaflops, billions of operations per second. I don't know what specific sort of computer hardware gets used these days, but it's probably something like a GPU, a graphics processing unit, from even just a high-end desktop machine nowadays. It's got quite a lot of megaflops or even gigaflop range if you get a bunch of them together. So it's probably not custom-built computer hardware these days, but an NVIDIA or ATI graphics card that has been reprogrammed to do math really fast for this AO system instead of creating a beautiful three-dimensional scene for a game.
All right. I was thinking back in my mind to the Star Wars, the Strategic Defense Initiative. In those days, we were being told that it would be in the teraflop range.
Oh, wow.
Trillion
operations per second.
Yeah, floating point operations per second. So very, very demanding.
Indeed, right.
And that was, in those days, beyond what we could do, or certainly beyond what we could put in orbit. As you know, one of the problems of putting a computer in orbit is that it has to be radiation hard, and we didn't have CPUs
right. All
like
those
that.
Particles flying around that the magnetic field of the Earth protects us from end up messing with your circuitry.
Yeah.
So and yeah, in the SDI context, you wouldn't have time to transmit your data back down to a supercomputer on Earth and do the calculations. I guess for a ground-based laser, you would have that option, but if you were had an orbiting battle station, putting a computer up there would be quite challenging.
Well, one suggestion was to put a large mirror in orbit and then keep the laser in the computers on the ground.
Oh, okay, so, and just bounce it to wherever
right.
you needed to shoot something down.
Yeah.
So probably would have worked, but we never quite came to that.
No, maybe fortunately.
Probably would have.
The problem resolved itself on a political level.
Right, exactly.
Yeah. Wow, very impressive. All right. Well, Brad, thank you so much.
My pleasure.
Right. And thank you for joining us here at Around Space. This is Dr. Bradford Behr. He's an astronomer and optical engineer working in the private sector, bringing spectroscopy down to Earth. Thank you very much, and see you again next time.